Mesh loop analysis with voltage sources only. 1. Mesh / loop analysis converts KVL voltage paths / loops into mesh / loop currents. For a one loop circuit, it makes physical sense. Since because a single loop only has one current. In this case, let's define the current IA. So if I look at a circuit, it's going to look something like this. I'm going to have an element, or a series of elements, so if I look at these elements and there's only one loop, then they all must have the same current. So let's say that the direction of the current is moving in this direction right here. And I'm going to call this loop current IA. So when I look at the polarities of these, that means here, if I have resistors, that must mean this right here. Oops. And I should be calling this 3, not 2. So in this case, we say that we have a loop current or a mesh current that we have defined as IA. But for multiple loop circuits, these loop currents are still present. For a 3 loop circuit, there are 3 loop currents. And in this case, I'll call them IA, IB, IC. So now if I do the exact same circuit, but then I add multiple loops, then we have something like this. I'm going to have a series of loops, and I'll start color coding these loops. Now note, I'm not specifically drawing resistors here, because in AC circuit, it actually does not matter what actually happens. Now, look at the way I'm going to color code these guys. So if I have an isolated loop, let's say the red ones, I would say that these elements are isolated, and these other elements over here are isolated from other loops. And then over here, this is isolated from other loops. But there are elements that connect two loops together. And so what I'm saying here is that there is a loop current, just like up above, that we call IA. I also have another loop current, very similar to above, which I'll call IB. And then I have a third loop current, again, similar to above, which I'll call IC here. So if I start labeling these, how about if we do what we did above here? I'll call this 1, 2, 3, 4. Now this will be 5, 6, 7, 8. So there are 3 loop currents that we can account for because of the single loop here. Now, it turns out that there are 2 situations. There are 2 situations for possible loop currents. There are isolated elements. So if I look at this isolated element, note that I have a loop for IA. So if I now copy this and bring it down, what you're going to find here is that let me paste this guy in here so you could see what I'm talking about right here. And what you're seeing here is that elements that are isolated to a single loop only experience one current flowing through them. In this case, elements 1 and 4 have current have a current IA flowing through them. So just for a bit of organization here, I'm going to move this guy down and put it right here. That's what happens if you have an isolated loop. However, there are these things called mutual elements. So in this situation, I would go up and I would grab this circuit right here. And I would put this down here. So what happens in this situation? Note that elements 2 and 3, for example, as well as 7, they are connected to other loops. So in this situation, we say that elements connected by 2 loops have superimposed currents. For example, there are 2 currents flowing, and in this case, it would be IA and IB through element 2. There are as well as 2 currents through element 3. In this situation, we would have IA and IC and 2 currents through element 7. And in this situation, it's going to be IB and IC. However, the actual currents through these mutual elements is a superposition of currents. So what do I mean by that? So let me bring this down just a little bit to clean it up. And then I would say this. So when I look at that circuit here, I'm going to go in and I'm going to modify the circuit. So we only care about mutual elements. We've already dealt with isolated elements, so I'm only looking at the grays. So look what I'm going to do here. So this implies that I only focus on gray elements. So look what I'm going to do. I'm going to go modify the circuit. So look what happens. I'm going to take IA, and then if I focus on this, that means I have IA flowing through 2, IA flowing through 2, because it's a single loop. Now, if I look at the B loop, that means here that I have IB also flowing through 2, and I have IB flowing through 7. So when I look at the loop at the bottom, which is IC, that means here that I have IC flowing through 3, and I also have IC flowing through 7. So what that tells me here is that the actual current, so let me say, so the actual currents, as we already said, are superpositions, are I2. So if I look at I2, it has to be a combination of IA. It's arbitrary how I pick the signs, by the way. In this case, I'm going to say it's I minus B because they're moving in opposite directions. Now, if I look at element 3 here, again, I pick arbitrary directions. I'm going to say that this is IA minus IC with the minus sign. And then if I go to I7, it's going to be the exact same thing. Maybe in this situation, we pick IB to be positive and IC to be negative. The sign convention is arbitrary. The mathematics are going to tell you. So when we look at these actual currents, I would say that these real currents are a superposition of loop currents. I know I've said that before, but this is really saying that, believe it or not, loop currents are real physical currents that one measures in a circuit. I'll be frank, when I first saw this, somebody told me that, I didn't really believe it. But it's amazing that it's really true. So then let's go to the second piece. The goal of mesh slash loop analysis is applying KVL to each loop to generate a system of loop current equations. If all loop currents are known, then one can calculate all the voltages, currents, and powers for the circuit. So we can break this down into 3 possible situations. How one uses loop analysis depends on the type of sources in a circuit. And this shouldn't be a surprise because when we did node analysis, we started with current sources. It had a very particular form. And then when we included voltage sources in the circuit, it changed how we did node analysis. The same thing happens with mesh. In this case, the three cases are is that we have independent voltage sources. That turns out to be the easiest. Then we increase the complexity by dealing with independent current sources. And then finally, we then do dependent sources, which is the most challenging one. Okay, so let's do mesh/loop analysis with voltage sources only. Why? Because it's the easiest case.